In this video, we're going to look at our final example on using the second derivative test to find the local extrema for a function. So we're looking here at this example number 9. And it says use that second derivative test to find the local extrema for the function f of x equals x to the 5 minus 5x to the 3. All right, so in order to use the second derivative test to find local extrema, we first have to talk about what that second derivative test tells us about maximum or minimums on our curve. So if we found our critical points, say we found them to be here and here, and then we ask our second derivative if our graph is concave up or down, say down here, up here, how does that tell us if these critical values are minimums or maximums? Well, we see from the image, which suggests the following. If our graph is concave down, then that critical point is going to be a max, a local max. If our graph is concave up, then that point will be a local min. So for this problem, we're first going to find those critical values using the first derivative. Then we're going to find or use the second derivative to tell us if those critical values are mins or max based on the concavity of that second derivative. All right, let's go ahead and get started. So first step we need to do is find the first derivative. So f prime of x should be the following. So we just have a difference with power functions. So we use that power rule to write our derivative as 5x to the 4th minus 5 times 3, which is 15, x squared. So now we want to know those critical values. So we want to know where that derivative is not defined or 0. We see that the graph, this function, the second derivative rather, can be evaluated at any x value. So there's no values where our function is undefined. So we just need to ask where 5x to the 4th minus 15x squared is equal to 0. So to do that, we can factor out a 5 and an x squared from each term. So that leaves us with that leaves us with x squared minus 3 equals 0. So if this product is equal to 0, then that means either x is equal to 0 or x squared minus 3 equals 0. So that second equation would tell us that x squared is equal to positive 3, which taking the square root tells us that x is equal to plus or minus root 3. So here what we just found are 3 critical values of our original function, meaning 3 values in which our function has a local maximum or minimum. So I'm going to draw out a number line just to keep track of everything I have. So I'm going to mark these critical values: 0, positive root 3, and negative root 3. So now what we're going to do is we want to know, is our function concave up, concave down, or maybe neither at these points? So to do that, I only need to test the second derivative. If I determine what the sign of my second derivative is at each of these points, then that sign, for positive, for example, concave up, will tell me what my min or max is. So first, let's compute that second derivative. So for s, f double prime of x is going to be, well, just the derivative of our derivative. So that would be 20x to the 3rd power minus 30x. So let's test those critical values at let's test each of those critical values on our second derivative. So I want to determine f double prime of negative root 3, f double prime of positive root 3, and f double prime of 0. So go ahead and pause the video and just work out each of those outputs for each of these critical values in our second derivative. So what we should be getting for f double prime of negative square root of 3 is negative 30 root 3. For f of square root of 3, we should be getting 30 root 3. And for f of 0, we should be getting 0. So what does this tell us so far? Well, we know the second derivative at negative root 3 was negative, rather. So our second derivative, f double prime, is negative. So that means our original function, well, it looks like this, concave down. So do we have a local min or max? We have a local max. So I'm going to write that, local max. Similarly, well, a little different, but in a similar way, f double prime of positive square root of 3 is 30 root 3, which is positive. So that means our second derivative is positive, which means our graph is concave up, which means our original function has a local min. So now what about f double prime of 0 is 0? Well, unfortunately, that doesn't give us any information about the concavity of our graph. So this information is inconclusive. So when it's the case that the second derivative is inconclusive, we need to then consult the first derivative again. And to consult the first derivative, we want to know, well, is our graph increasing and decreasing around that critical point, which would mean a maximum, or decreasing, increasing around that point, which would mean a minimum, or is maybe our graph increasing and increasing, which means that 0 input is not a local max or min. So essentially, we just need to go back and use the first derivative test. So I'm going to pick a number to the left and right of 0. So I could do -1 and 1. And I'm going to ask my derivative now for the output values of each of those inputs. So -1, I'd be getting 5 times -1 to the 4th, which would just be 1, so 5, minus 15, which would be -10. Similarly, if I plugged in 1, I would be getting 5 minus 15, which is -10. So in each case, my derivative is negative, which means that on this interval surrounding 0, my graph is decreasing and then decreasing. So for us, this would imply at x equals 0, f of x has no local max or min. So then we can summarize here. At x equals -√3, f is concave down, which implies that the input value, x equals -3, is at a maximum. So it implies a local max at x equals -√3. And in a similar way, at x equals +√3, f is concave up, which implies that we have a local min at x equals +√3. All right, and before we're finished here, let's go ahead and graph this function so that we can see this behavior on a graph. So I'm going to go over to my Desmos graphing calculator, and I've put in my original function here. And we can see that our critical points are here at -√3, +√3, and 0. And are we expecting this behavior? Awesome. Yes, so local max at -√3, local min at +√3, and then no local max or min at 0. So I encourage you to please graph this on your own so you can see this behavior and you can become more familiar with graphing. And also draw a little sketch of this graph on your notes so that you can refer to it later. All right, great work, everyone. Thank you for watching.